Hi everyone. Today we start a new topic. This is a theorem for three lectures. So this is the beginning of of the topic. It's Plunnecke-Rusza inequalities. Well, what is our aim? Main result is this one, but we cannot prove it today. Well, it's quite lengthy. Suppose x a1 an subset G finite non-empty subsets of an abelian group. Well, this is the fact that the group is abelian is very important for this result. Actually, it's not true when the group is not abelian. So we substantially use this fact that group is abelian, and well, as I said, it's not working otherwise. Well, then if x plus a1 is alpha 1 x, x plus a2 is alpha 2 x, alpha x plus an is alpha n x, then there exists a subset. Then there exists subset x prime non-empty. There exists non-empty subset x prime such that a1 x prime plus a1 plus an is smaller or equal than alpha 1 alpha m by x prime. Well, if we rewrite it, it would be x plus a1 x plus an by x in the n by x prime. Well, this is a general statement of the Plunnecke-Rusza inequalities. Why I wrote here inequalities, not inequality, just because there are lots of versions of this Plunnecke-Rusza result, and I state some of them, but not today. This theorem is proved through oriented graph techniques, through so-called Plunnecke graph. Well, first what we do, this proof takes about 2-3 lectures. I think 3. More likely it would be 3 lectures, not 2. Well, and then I'll give you one application of this result, because this is quite powerful technique of proving theorems in additive combinatorics. Well, that's why I'm giving this theorem to you. Well, what we do now? First, I just give you. Well, it's worse version of this inequalities for the case. Well, what the problem with this? We don't know what this X prime. We know this X prime exists. We don't even know what the size of X prime. We can control its size. It's unknown subset, and for applications it's bad. For most applications it can be used. So there are versions of Plunnecke-Rusza inequalities where this X prime erased. How to erase this X prime? Simply we do this. we worsen here. We worsen inequalities in here, and now we use Plunnecke-Rusza. And it's smaller or equal than X prime is subset of X, so size of X prime is at most size of X. So it's at most right? So this worsened version of the inequality, inversed version of an inequality is the most frequently used version. It's version without unknown subsets. Well, but this is simply corollary of this one. So we'll prove this version, and this follows from that version. Well, okay. Well, what next? Next, I'll show you. So this is most frequently used type of the Plunnecke-Rusza inequalities. Well, good. First theorem we prove. This is one. It's Ruja triangle inequality. Ruja triangle. Huh? No, well, this is a partial version of this actually. This is quite a simple result, which is sometimes used instead of this. So we use either this or this. So we need, actually, this is independent result, but we need both of them. Ruja triangle inequality says if A, B, C subset of G, finite non-empty, subset of an abelian group G of abelian group G. Then A minus C is at most A minus B by C, B minus C divided by B. Just like that. So, so this inequality for A minus B actually. Mostly we use it for A minus B. Well, and this is for A plus B. So we need both of them. Proof. How to prove this? Well, we have to build. We build an injection F from A minus C times B onto A minus B times B minus C. Well, how to build this injection? First, we just number somehow the elements of B. Let's take any numbering. Take any numbering. Well, now for D in A minus C, we take, look, there are few representation of the type A minus C, right? So we know that if the in A minus C, there are at least one such representation, right? So, but there can be not only one, right? So what we do, we just take AD, CD, where AD is the minimal, minimal by the number, is the minimal by the number, element A from A among all the possible representation of G, representations of G among all the representations of type G is equal A minus C, A in A, C in C. Well, we take all the possible representations and choose one with minimal index of A. We fix such representation for each T. Okay, now, now here is our function. Yeah, by the way, when we fix AD, CD is defined uniquely, right? So CD is D minus AD. So if we fix D and AD, CD is defined by this formula. Right. Well. Here is our injection. It takes pair D from A minus C and B from B. And it returns this one, AD minus B and B minus CD. Good. Why it's injection? Well, it's element of A minus B times B minus C, right? Well, why this is injection? Just because, well, let's check. Suppose f of d1 b1 equals to f of d2 b2. Well, then this means a d first, d second. Let's denote this way. It's d1 e. No. We don't need it. It's a d1 minus b1, the pair a d1 minus b1 and b1 minus c d1 equals to pair a d2 minus b2 and b2 minus c2, b2 minus cd2, right? This means that ad1 minus b1 equals to b1 minus cd1, and also ad2 minus b2 equals to b2 minus cd2. Okay. What we know? What do we know? Well, what we can do? We can. Sorry. I didn't. I wrote everything incorrect. Naturally, first component equals to this first component. This component equals to this component. Sorry, that's my mistake. B1 minus CD1. Right, this one. Well, look. Now add two equations, right? So this is equal. Well, follows from this follows that a d1 minus cd1 equals to ad2 minus cd2, right? Just add these two equalities. Well, ad1 minus bd1 b1 equals ad2 minus b2, right? Well, from this follows, remember we fixed one representation for each element. So if this representation are equal, then they represent one element. So D1 follows. This is D1, this is D2. So D1 equals to D2, and this follows. D1 equals to D2, B A D1 equals to A D2, because we fixed one unique representation, right? And B D1 equals to B D2. Oh, see, I see, yeah, see D1. See D2, right? So if we add them, then D1 cancels. Yeah, that's what we do. CD1 is equal to AD2 minus CD2. But I don't understand how we are getting the. So when we have only one equation, if we add those two. When we add, we have to leave one equation untouched and change one another. So this is main technique. We can add two rows of matrix or two columns of matrix, but we change one column and we don't touch another one. So just you have to choose which row you don't change. Well, look, so this is D1, this is D2. We fix one representation, so AD1 equals to AD2, CD1 equals CD2, and from this follows B1 equals B2. And B1 equals B2. So from this follows that F is injection. Well, since there are injection between this set, between this set and this set is at most that set, right? So from A minus C times B onto A minus B times B minus C. So this means that A minus C times B is smaller or equal, the size of this set smaller or equal in size than A minus B and B minus C. Well, this is Ruja triangle inequality. So good. I also can give you a short proof of this Plunnecke-Rusza inequalities. Well, this inequality in case when A1 equals to A2 to AN, when all the sets are equal A1 AN. Well, this is also quite frequently used case, and well, I'll state this theorem for you. Well, theorem 3. Right, theorem 3 says that there are, well, if A, X, A subset of G finite non-empty, subsets of an abelian group. Then we have this one. Then for any k, which is at least one, then if, if x plus a is, say, alpha x, then there exists a subset x prime. Then for any natural k which is greater or equal than 1, and there exists one, sorry, again incorrect. In the beginning, this order of quanters, there exists universal x prime, non-empty x prime, which is universal for any k. This is more powerful than I stated before. There exists a universal x prime such that for any k greater or equal than 1, k natural number, we have x plus ka is at most alpha in the k by x prime. Why it's a partial case of general Plunnecke-Rusza inequalities? Just because, well, look, alpha, it's x plus a divided by x. Well, in the kth power, this is version of Plunnecke-Rusza when a or the a are equals. Do you know what ka is? It's a plus a k times. That's why this is a partial case of general inequality. Well, this theorem is proved by Petridis. So first, here is a history of the question. Well, there was a publication of the German mathematician Plunnecke, which was published, but as far as I know, I didn't see this publication. It was in German, and everyone who read that paper, it was about graphs. It was about specific graphs and specific behavior inside this graph. So it wasn't about some set. Ruja, the Hungarian mathematician, took this publication, consulted with Plunnecke, and understood what he proved, and gave a shorter, more understandable proof of his result. And also gave an implication in the form of Plunnecke-Rusza inequalities. So basically, this is Ruja's result. But as far as I know, he made somehow this with consultations with Plunnecke. So probably Plunnecke somehow take place, somehow work with Ruja when he wrote this paper. So then Petridis, it's quite 2017, just found a shorter proof without graphs of Plunnecke-Rusza result, without when in the case when all the sets are equal. I tried to apply his method to different sets. Unfortunately, it's not working well. But for equal sets, it gives even more powerful result, because in general case with graphs, we cannot prove that for any k there are one unique universal X prime. In general proof, we see that this X prime depends on number of sets. But here, this X prime doesn't depend on number of sets. It's one, the same for any natural key. Okay. In order to prove that, we need lemma, one lemma. Suppose that x x a b is such finite non-empty xa 1 minute. Yeah, xb finite non-empty subsets of an abelian group G such that for any non-empty subset Z of x, x plus b by b is the smallest meaning for the fraction z plus b by by x, here by z. So x and b is such subsets such that this fraction has minimal meaning over all the subsets, non-empty subsets of z of x. Well, then for any c subset of G, finite non-empty, x plus b plus c is at most x plus b by x plus c divided by x. Well, yeah, right. We need this lemma. See, here x is very, very specific subset with this property. That's why we don't need come to subset of x. Well, we take and we number somehow all the elements of C. Somehow number all the elements of C. Well, and we now do this, well, x plus b, x plus c, sorry, x plus c Let's work with this set. Well, first, represent it as union of for I1 till R Ci plus X, right? That's true. But, well, this union is intersecting union. This set can intersect, right? Because, well, each element from X plus C can have more than one representation of this type. How to remove these intersections? Well, we just have to introduce subsets xy, which are all the x from x such that look, ci plus x small doesn't belong to C0, C1, C I minus 1. It's for I strictly greater than 1, x1 is x. For I strictly greater than 1, xi is this one. All the x from x such that ci plus x is not element of c1 ci minus 1 plus x. This is a set x small. It's well, this is notation for the element, right? I just put bars onto x in order to distinguish them. Okay. What we do? We just take inside x only unique elements which appear in Ci plus x. All the elements which we already obtained in previous steps, when we unite them, we remove them outside. We just take them, when we remove this out from the set, them out from the set. Right?
So you are saying that you're taking only those ones that we got in the union in the experiment.
Yeah. This is union for, but this is non-intersecting union. Ci plus xi, right? That's what we do. We represent this intersecting union as non-intersecting union. But these subset xi's are, we don't know what the sets are, right? Xi's are intersecting, but Ci plus Xi non-intersecting, right? Their shifts by Ci are non-intersecting, but Xi naturally can intersect because they are all subsets of X. Right? Good? Understand? Okay. So since they non-intersecting, so x plus c is some cardinality of x plus c is sum of for I 1 to r ci plus xi. So, but this shift by one element, so this is sum for I from 1 till r xi. Right? Moreover, look. Look. What can we say? More even more. We can say this. C. Yeah, we can say this. C1, C I minus 1 plus x is equal to what? Yeah, this is a non-intersecting union for I from J till 1, from 1 till A, till I, right? Till, yeah, like this. From J, from 1 till I, xi plus, no, ci plus x, I. Even part of this sum set is also non-intersecting union, right? So which means that cardinality of C1 Ci plus x is sum of for J equals to 1 till I x i's xj's. Good. Well, now here, well, let's denote x r complement. This is x minus xr. So for this xr complement, we take complement to x, not to the group, but to x. What can we say about xr? We can say that c plus xr, cr plus xr complement is what? Is subset. Is subset of c1 cr minus 1 plus x. Right? Do you understand?
That's also we're taking complement of XR, right? It should not be X.
It must be subset of this, right? Because all the elements which outside this set are inside the set CR plus XR, right? So what can we say? We can say that CR plus XR plus B, XR complement plus B, is subset of C1 CR minus 1 plus X plus B, right? Good. Now, our aim is to estimate this set. Now let's take this set. Let's take this set x plus b plus c is equal to, this is union for, it says union for C1 CR minus 1 plus X plus B union what? Union what? Union CR plus X plus B minus what? Minus set this one. Why I wrote this this set, I represented this set in this way. Well, look here. I didn't write down CR plus XR plus B. I wrote CR plus X plus B minus this set because I also want non-intersecting representation, non-intersecting union here. And this is non-intersecting union, but CR plus XR plus B is, well, CR plus XR is non-intersecting with this one, right? C1 CR minus 1 plus X. But CR plus XR plus B can intersect with this set. This is possible. So how to remove all the elements outside from this set? We have to remove this subset. Good? Do you understand? Well, so well, now we use induction on R. Base. C equals to 1. C is one element set. Then, X plus B plus C has cardinality X plus B. And this is equal to X plus B plus X plus C divided by X, right? Step, inductive step. Well, we suppose that C1 CR minus 1 plus X plus B. Well, what is this? This is at most, by our supposition that it is at most, C1 CR minus 1 by plus X by X plus B divided by X. Okay, now we use our supposition, right? Look here, this one. Look here, look in here. We use this one. So this is sum for I equals 1 till r minus 1 xi by x plus b divided by x. Now, well, actually with this part, we finished with this part. So now, x plus b plus c equals 2 c1 cr minus 1 plus x plus b plus cr plus x plus b without cr plus xr complement plus b, because this is non-intersecting union. Right? Good. Well, look here. We estimated this part, so this is at most x plus b by x by sum for I from 1 till r minus 1 x's. Now let's estimate this part. So what is this? It's x plus b. This cr plus xr plus b subset of cr plus x plus b. So this is x plus b minus cardinality of this one, cardinality of xr complement plus b. How to estimate this xr complement plus b? We use this condition, because xr complement is any subset of x, right? We can substitute xr complement instead of z here. So x plus b by x is at most xr complement plus b by xr complement. Which means that xr plus b complement is at least x plus b by x by xr complement, right? So this is lower bound for xr plus b, but for minus xr plus b it's upper bound, right? So this is upper bound of the form x plus b by x by sum for x x's I from 1 till r minus 1 plus x plus b by x by x minus xr complement, right? Right? But x minus xr complement is xr. So this is x plus b by sum of x I from I till r x size, which is x plus c. Good. So this is all. Okay. I want to array this. so better erase that one. Now we have to. Now we're ready to prove theorem 3. Now we're ready to prove this theorem. Look, naturally we use induction by K, induction on K. Well, we have to introduce x prime. What is this x prime? Suppose x prime and then induction on K. Suppose x prime, non-empty subset of x is such subset that x prime divided by plus x plus a divided by x prime is at most z plus a divided by z for any z subset x non-empty. We just take such subset x prime such that this fraction takes minimal meaning. Well, this x prime exists because there are finitely many such subsets of x prime. So we just take among all these finitely many meanings the minimal one and take subset where this meaning of the fraction is attained, right? Well, this x prime is our x in the lemma. Now induction on K. Right. Base. K equals to 1, then x prime plus a is at most what? Well, this is at most this is true for any subset z of x. So we can take any subset. Just take z equals to x. So this is at most x plus a divided by x prime. But x plus a divided by x is alpha. So alpha x prime. That's all we need. Even more. Well, no, we cannot say more. Inductive step. Well, suppose we prove this inequality for k minus 1. Let's prove for k. Suppose that for k at least 2, x plus x prime plus k minus 1a is at most alpha k minus 1 by x prime. Right. Well, let's take x prime plus k minus 1, a plus a by lemma 1, look, by lemma 1, x prime falls under condition of lemma 1, right? It satisfies condition of lemma 1. So we can use lemma 1, and it says that this is at most x plus k minus 1 by x plus a by x. But, sorry, k minus 1a. This is x prime, this is x prime, and this is also x prime. Look here, x prime plus x divided by x prime is at most z plus a by z for any subset z. We can substitute here anything, so we substitute here x. So we just take, well, for this part we apply supposition, inductive supposition. So a k minus 1 by x prime. For this one we estimated by our by construction of x prime. It's at most x plus a divided by x, which is alpha. So this is alpha in the k by x prime. Well, that's all we need, right? The theorem is proved. This is a method of Petridis. It's not using graphs when all uses only induction, and well, it gives a short, elegant proof of a Plunnecke-Rusza for equal sets. Okay. Now, what we do next? I start introducing what is Plunnecke graph, what the result of Plunnecke we're going to prove. After we prove theorem of Plunnecke, well, I have to introduce some notations and some definitions in order to state his theorem. We start proving Plunnecke theorem. When we proving Plunnecke theorem, I'll give you application of this Plunnecke theorem, and I give you second proof of this Petridis result. But this x prime won't be a weaker version of this result with non-universal prime, which we cannot prove with Plunnecke method that this x prime is universal for any HLK. Okay, but I'll give you second proof actually of this, and then I unite this proof onto different sets. Well, this program. Well, let's start. Plunnecke graphs. Well, what is Plunnecke graph? First, definition. Graph G, the graph, which is this is oriented graph remember that, the oriented graph, the oriented graph. Graph G, vertices, edges, is called H-level graph. If H is at least 1. If no, it is at least 0. If V is union, it's non-intersecting union. This is notation for non-intersecting union. Non-intersecting union from I from 0 till H, Vi. So this is non-intersecting union of VI's, which are our levels actually. V0, V1, VH. So we have these levels. Look here. Pay attention, please. We call this graph H level, but it has H plus 1 level, 0 till H. That's why we can take 0 level graph, which has 1 level actually. So, and H is subset of V0 product V1 union V1 product V2 V H minus 1 product VH. So the edges, all the edges go in between consecutive levels. Right? This is H-level graph, oriented graph, in which we can split all the vertices onto levels, such that all the levels are non-intersecting and edges go in between consecutive levels. Good, right? Okay, what is Plunnecke graph? Definition. H-level graph is called Plunnecke graph if this is a part when I draw pictures. Okay, first picture. After I draw picture, I'll give you a formal definition. First picture. From this, if we have this configuration, we must find this configuration. Well, let's denote this somehow. U, V, W1, W2, W3, WK. We must find this configuration. This is U. This is U1, U2, U3, UK, W1, W2, W3, WK. If we have this configuration, we must find the U1 UK such that we have this configuration. Good. Formally, for any I from 1 till h-1, for any u from vi-1, for any v from vi, and for any w1 wk from vi plus 1. There exists, we can find such that uv is an edge and vw1, vwk are edges. We can find u1 uk from vi such that u v1 u vk are edges, and also vi v1 w1 vk wk are also edges. This is first picture. This is first condition. Second condition. If we have such configuration, then we must find such configuration. We must find such configuration. We must find such configuration. Do you need to introduce it. Do you understand how to introduce this formally? The same way for any levels, for any U, V, W, for any U1, UK, for any V, only W, we can find V1, VK such that all these are edges. Okay, this is Plunnecke graph. The graph, the H-level graph, which satisfies these two conditions. Also. Right. Well, let's. I think I've got time to give you example of Plunnecke graph, and then we continue with this topic with Plunnecke graphs next lecture. Okay, example. Example is addition graph. Well, addition graph. Well, what is this? A, B, subset G, finite non-empty, sets of abelian group G, or an abelian group G. Here, the zero level of this graph is A times 0. First level of this graph is A plus B times 1. Why we introduce a second component in order to separate these two sets? We need these levels to be non-intersecting, right? But A and A plus B not necessarily non-intersecting set, right? So we introduce the second component. Till H. Here's our levels. What is our vertices? Our vertices is here. Each vertex represent any element of A. This in here, each vertex represent any element of A plus B. In here, each vertex represent any element of A plus 2B, and so on and so forth. So each level larger than previous one. Right. What are edges of this graph? Well, we draw C, D is edge of the graph. If and only if C belongs to A plus IB by I, D belongs to A plus I with A plus 1B times I plus 1, I 1, 0 till H minus 1, right? And also not only this, but also this first component, difference of first component C is C. How to know this? It's pair x I, d is y I plus 1, right? And difference of these two guys, y minus x, belongs to B. This is edges of this graph. Do you understand how it works? We just take any element from here, add here any element from B. We have cardinality would be different arrows here, and do that for each element of A. The same for first level, and so on and so forth. Incoming, huh?
Just to confirm, Prof, so when we're saying level, we are actually saying different particle sets, right? Like B is equal to R is equal to H, B and B. Like we are considering different sets.
Yeah. Well, this different sets because, well, we multiply them by each. Otherwise, they can intersect, and this formally this is not levels. These are not levels. Well, 1 minute left. Okay. Do you understand how what is graph? What this graph is? Okay. Why this Plunnecke graph? Well, suppose we have such configuration. Suppose we have such configuration U, V, in this graph, in this particular graph, W1, W2, W3, WK. So we have V minus U in B is in B, right? And W1 minus V. I just remove the second component, but sorry, but if I do this more formal way, it takes even more time. Sorry for that. These are also in B, right? Just do this. V minus U plus W1 minus V minus V. This is what? This is V minus W, W1. Yeah, no, W1 minus U, right? Right. Well, okay. I'm sorry, I just my head working bad when we have a lack of time. Sorry, just let's finish for today, and I'll prove everything next lecture. Okay, questions? I have to repeat this example, unfortunately, but okay. Bye. I remember that, sorry. This is B, look here, and this is B1, BK. Look here. B plus B1 What is this? Huh? Well, look. U plus B plus B1, what is this? It's W1, right? Now we have to do this. Here we use commutativity inside the group. U plus B1, it's also W1. And this is our V1. Right? Okay. Sorry, probably you don't have time to understand everything. Let's finish.